Brain rewiring and cognitive transformation. Think like a genius hookah. Everything you've been taught about intelligence is wrong, not slightly off, not a little outdated, fundamentally, structurally, dangerously wrong. You were told, probably in a classroom, probably by someone well-meaning, that some people are just smarter than others. That genius is a gift, that your brain, by some cosmic lottery, either has it or it doesn't. And if you happen to land on the wrong side of that lottery, well, you'd better find something else to be good at. Here's the thing. That idea isn't just discouraging. It's not supported by neuroscience. It's not supported by cognitive psychology. And it's definitely not supported by the life of the man this channel is built around. Richard Feynman, who as a young student had an IQ score that his colleagues later described as merely respectable. Not extraordinary, not genius tier, respectable. And yet Feynman became one of the most creative scientific minds of the 20th century. He rewrote quantum electrodynamics. He cracked safes at Los Alamos for fun. He learned to draw. He learned to play bongo drums professionally. He taught himself biology, chemistry, and computer science deep enough to publish original insights in all three fields. And when people asked him how, he didn't say, "I was born this way." He described a set of practices, habits, ways of approaching problems that he had deliberately, consciously built into the architecture of his thinking over decades. That's the subject of today's video. Not inspiration, not motivation. The actual, concrete, neurologically grounded methods for rewiring your brain's thinking patterns, and why Feynman's approach, far ahead of its time, maps almost perfectly onto what modern neuroscience now tells us about how transformation actually happens. Stop. Think about that for a moment. The most celebrated intuitive genius of the modern era was, in a very real sense, a self-made thinker. And the road he traveled is open to you. Contrast. Bridge. Let's start with some context because this conversation lives at the intersection of two fields that didn't used to talk to each other very much: physics education and cognitive neuroscience. For most of the 20th century, the brain was treated a little like a computer that came preloaded with fixed software. You could add data, facts, skills, memories, but the underlying operating system, the hardware of your cognition, was more or less locked in place by the time you hit adulthood. This view had a name, neural fixism, and it was the dominant paradigm in neuroscience for a very long time. Then, in the 1990s, something cracked open. Researchers began documenting something they called neuroplasticity, the brain's lifelong ability to physically reorganize itself in response to experience, not metaphorically reorganize, literally, new synaptic connections forming, old ones pruning away. Gray matter density visibly shifting in response to sustained practice. London taxi drivers, who spend years memorizing thousands of streets, showed measurably enlarged hippocampi, the brain region associated with spatial navigation. Musicians who practiced for decades developed thicker cortical representations of their playing hand. Meditators who logged thousands of hours showed structural changes in regions governing attention and emotional regulation. The brain, it turns out, is not a computer with fixed software. It's closer to a living forest, constantly growing, constantly dying back, constantly reshaping itself around the paths you walk most often. And here's where Feynman enters the picture in a way that should make every educator sit up straight. Because long before neuroscientists had the imaging technology to see plasticity happening, Feynman had intuitively discovered and practiced a set of techniques that, we now understand, are precisely the kinds of activities that drive the most profound and lasting forms of neural reorganization. He wasn't just a great thinker. He was, without knowing the vocabulary for it, a practitioner of deliberate cognitive transformation. And the principles he used are teachable, they are learnable, and they work. Core explanation. So what does it actually mean to rewire your brain? Let's build this carefully because the concept is thrown around so loosely in pop psychology that it's lost almost all meaning. When neuroscientists talk about rewiring, they're talking about changes that happen at the level of individual neurons and the connections between them. A neuron is just a cell, but it's a cell with an extraordinary property. It can grow new branches called dendrites that reach out toward other neurons. When two neurons fire at roughly the same time repeatedly, the connection between them strengthens. When they stop firing together, the connection weakens and eventually disappears. This is the mechanism behind what neuroscientist Donald Hebb summarized as neurons that fire together, wired together. Now here's the thought experiment. Imagine your current thinking patterns as a network of hiking trails through a forest. The trails you walk every day are wide, clear, easy to follow. You can navigate them in the dark. These are your habitual ways of thinking, your default assumptions, your automatic responses, your comfortable mental grooves. For most people educated in traditional systems, these trails were carved by others, teachers, textbooks, standardized tests, the cultural pressure to find the one right answer rather than to explore the landscape. Now imagine you want to build a new trail to a part of the forest no trail currently reaches. At first, you're pushing through undergrowth. It's slow. It's effortful. Your brain actively resists it. This is a very real neurological phenomenon called cognitive inertia. The brain prefers energy efficiency, and the old trails are energetically cheaper than cutting new ones. But if you walk that new path consistently, something remarkable happens. The undergrowth starts to clear. The path widens. Neurons that were never connected before begin firing in new combinations. And eventually, this is the part that still astonishes neuroscientists, the new path can become as automatic, as natural, as deeply grooved as the old ones. This is what Feynman did, not once, not accidentally, systematically throughout his entire life. But here's where it gets interesting. The paths Feynman built weren't random. They followed a very specific architecture. And that architecture is what we need to understand if we want to replicate the results. The first principle Feynman operated by and stated explicitly many times was this: if you cannot explain something simply, you do not understand it yet. This isn't just a clever aphorism, it's a neurological claim. When you truly understand something, you've built multiple redundant representations of it in your brain. Visual, spatial, linguistic, procedural. We can approach it from different angles. You can translate it into different forms. But when you only have a surface-level familiarity, you have one representation, the words you were taught, the vocabulary, the formula, and the moment someone asks you to explain it differently, the illusion collapses. Traditional education, tragically, trains people primarily to acquire that single representation. You learn the name of the thing. You learn the formula for the thing. You learn enough to pass the test about the thing, and then you move on. What you almost never do, almost never, is sit with the thing long enough to build those multiple, redundant, deeply connected representations that constitute genuine understanding. Feynman called the alternative approach first principles thinking. Strip away everything you've been told. Go back to the raw phenomena. Ask not, what is the accepted explanation? But what would I have to conclude if I looked at this with completely fresh eyes? This is cognitively difficult. It requires dismantling mental structures that feel like knowledge, because they are labeled as knowledge, because they are encoded in confident, fluent-sounding language and revealing the emptiness underneath. It is, for most people, uncomfortable to the point of being aversive, and that discomfort is exactly where the rewiring begins. The second Feynman principle is what we might call productive confusion. Feynman was famous for spending long periods being visibly, deliberately confused. Not panicked, not defeated, curiously, almost playfully confused. He would sit with a problem that didn't resolve, turn it over, look at it from oblique angles, let it ferment. Modern cognitive science has a name for what's happening during these periods: diffuse thinking. It's the mode the brain enters when it's not actively forcing a solution, when it's in a kind of relaxed, wide-focus state. And it turns out that diffuse thinking is when the brain makes its most creative cross-domain connections, when neurons that don't usually communicate with each other start exploring new pathways, when the insight that feels like it arrives from nowhere actually arrives from the background processing your conscious mind didn't know is happening. Most people, trained by educational systems that reward speed and certainty, have a very low tolerance for diffuse thinking. They hit confusion and immediately reach for the answer, the textbook, the internet, the expert. They bypass the very cognitive state where the deepest learning happens. Feynman didn't do this. He sat with confusion the way a musician sits with a difficult passage, patiently, persistently, with something approaching affection for the difficulty. The third principle is cross-domain translation. Feynman learned biology. He learned art. He learned music. He learned safecracking. And he didn't learn these things as hobbies separate from his physics. He used them as lenses, as alternative vocabularies, as structural frameworks to illuminate what he already knew from new angles. When he thought about quantum behavior, he thought about it in terms of springs, waves, flowing water, little arrows spinning through space. He built an enormously rich cross-domain architecture of understanding that gave him more pathways into every problem than a specialist with narrow expertise would ever have. Neuroscientifically, this is the mechanism behind what researchers call transfer learning, the ability to apply insights from one domain to problems in another. And it is one of the most reliable markers of the kind of flexible, creative intelligence that distinguishes exceptional thinkers from merely competent ones. Deepening insight. Now, you might be thinking, this all sounds compelling, but how do I actually do it? How do I, a person with a job and limited time and a brain already full of existing habits, begin the process of genuine cognitive transformation? Let's get specific, because vague inspiration is cheap, and Feynman himself would have had very little patience for it. The first exercise is what's commonly called the Feynman Technique, though Feynman himself never labeled it as such. It goes like this. Take any concept you believe you understand. Write it down at the top of a blank page. Now explain it, in writing, out loud, however you prefer, as though you are teaching it to a 12-year-old who has no background in the subject. Not a smart 12-year-old, just a regular, curious kid. What happens next is the important part. You will hit a wall, a place where your explanation breaks down, where you reach for technical vocabulary because you don't actually have an intuitive model underneath it, where you realize that you know the words for the thing, but you don't understand the thing. That wall is not a failure. That wall is the beginning of real learning. Go back to primary sources, fill in the gap, try again, repeat until you can get all the way through without reaching for jargon as a crutch. This exercise done consistently builds a habit of genuine conceptual accountability. It rewires the brain to notice the difference between knowing and knowing the name of something, a distinction that, as Feynman's father famously taught him as a child, is one of the most important a thinker can make. The second exercise is deliberate confusion practice. Most people actively avoid topics they find confusing, which means they spend their entire cognitive lives inside their existing mental models, endlessly reinforcing the paths they already have. Deliberate confusion practice inverts this. You seek out the things that confuse you most. You sit with them. You don't immediately reach for the answer. You let your brain wrestle. Try this. Pick one genuinely confusing topic each week, something at the edge of your understanding, something that makes you feel that faint anxiety of not knowing. Set a timer for 20 minutes. No looking anything up. Just think about it. Turn it over. Ask yourself what you would need to know to begin to resolve the confusion. Ask yourself what assumptions you're making that might be wrong. Then, after the 20 minutes, explore. But the exploration will be richer, more motivated, more deeply encoded, because your brain has been actively reaching for it rather than passively receiving it. The third exercise targets the limiting mental habits formed by traditional education, specifically the habit of seeking the one right answer. Take any problem you're currently working on, in any domain of your life. Now generate 10 possible explanations or solutions, including ones that seem wrong. Not 5, 10. Force your brain past the first plausible answer, past the second, into the territory where you're genuinely stretching. This is a neurological workout for the prefrontal cortex, the region governing flexible, creative cognition, and like any workout, it gets easier and more productive with repetition. The fourth exercise is analogical mapping. Feynman was a master of this. Take a concept you want to understand deeply. Now find an analogy for it from a completely unrelated domain. Not just any analogy, a structural analogy, one that maps the relationships between the parts, not just the surface appearance. If you're trying to understand network effects in economics, find a physical phenomenon that works the same way. If you're trying to understand a biological process, find a mechanical analog. The effort of building the mapping, of finding where the analogy holds and crucially where it breaks down, is itself an extraordinarily powerful thinking exercise. It forces the construction of exactly the kind of multi-domain interconnected neural architecture that distinguishes flexible intelligence from brittle expertise. Now here's a deeper layer, that most discussions of Feynman's methods miss entirely. All of these practices have a common underlying structure. They all involve generation rather than reception. They all require your brain to produce something, an explanation, a question, an analogy, an alternative hypothesis, rather than simply absorbing something delivered from outside. And this distinction, generation versus reception, is one of the most robustly supported findings in cognitive science. Researchers call it the generation effect. Information that you generate yourself is encoded more deeply, retained longer, and more readily transferred to new contexts than information you passively receive. The act of struggling to produce something, even if you get it wrong, creates richer, more interconnected memory traces than the act of reading, listening, or watching, no matter how high quality the source. This is incidentally one of the most damning indictments of traditional lecture-based education. The format that dominates most schooling, expert speaks, students receive is precisely the format least aligned with how the brain actually builds deep, flexible, transferable knowledge. It is, neurologically speaking, among the least effective methods available, and yet it persists century after century because it is efficient for the transmitter rather than the receiver. Feynman knew this instinctively. He was a famously active, generative learner. He didn't attend seminars and take notes. He sat in the back and tried to derive everything himself before the speaker got there. He read papers by covering the conclusions and working out what they should be. He taught constantly, formally and informally, because he understood, before the vocabulary existed to describe it, that teaching is one of the most powerful forms of learning available. Building intuition deserves its own consideration here, because it's one of the most misunderstood aspects of expert cognition. People tend to think of intuition as mystical, as something you either have or you don't, as the province of geniuses who think in ways ordinary people can't access. Feynman himself contributed to this mystique somewhat. His intuitive leaps in physics were so rapid and apparently effortless that colleagues sometimes accused him of not being able to explain how he knew things. But cognitive scientists who study expertise have a very different picture of intuition. Researcher Gary Klein, psychologist Daniel Kahneman, and others have documented that expert intuition is not magic. It is pattern recognition operating below the threshold of conscious awareness, the rapid automatic deployment of a vast library of patterns built through years of accumulated varied experience. The chess grandmaster who sees the right move instantly isn't accessing supernatural intelligence. They've played so many games, analyzed so many positions, that the pattern activates before conscious deliberation has time to begin. Feynman had built, through decades of active, generative, cross-domain learning, a pattern library of extraordinary depth and breadth. When he looked at a new physics problem, he wasn't starting from scratch. He was matching it, below the level of awareness, against thousands of related structures he had encountered before, finding the family resemblance, the structural echo, the pattern that pointed toward the solution. This means intuition is trainable. It is the accumulated residue of quality practice. And the practices that build it most efficiently are exactly the ones Feynman used. Generative learning, deliberate confusion practice, cross-domain exploration, and the patient construction of deep conceptual understanding rather than surface familiarity. Mind-expanding conclusion. Let's zoom out now. Because what we've been talking about, in a sense, is more than just learning techniques. We've been talking about the relationship between a human being and their own mind. And that relationship, for most people, is surprisingly passive. Most people experience their thinking as something that happens to them, automatic, habitual, largely inherited from the environments and institutions that shape them. They don't experience themselves as the architects of their own cognition. They experience themselves as occupants of a mental house someone else built. What neuroplasticity reveals, what Feynman's life demonstrates, is that this passivity is optional. The house can be rebuilt. The trails through the forest can be redirected. The patterns of thought that feel as fixed and permanent as the landscape are, in fact, as revisible as any habit, any skill, any practiced behavior. This is not a small thing. It has implications that ripple outward from individual lives into the way we build schools, design workplaces, structure careers. If intelligence is not fixed, if the quality of your thinking is, to a very significant degree, a function of how you've practiced thinking, then the question of what we practice and how we practice it becomes one of the most important questions any individual, any institution, any society can ask. Feynman spent his life asking it, not always consciously, not always systematically, but in everything he did, in the way he approached problems, in the way he taught, in the restless curiosity that drove him across disciplines and domains. He was practicing and thereby demonstrating a vision of human cognition as something active, malleable, and endlessly improbable. And the beautiful, humble, and galvanizing implication is this: the gap between where your thinking is now and where it could be is not a function of your genes or your test scores or the accidents of your early education. It is a function of your practices, of the trails you choose to walk, of the confusion you choose to sit with, of the explanations you force yourself to generate rather than passively receive. You are not the fixed product of your past. You are a living system with the capacity to reorganize itself around the paths you walk most often. That's not a metaphor. That's neuroscience. That's the biology of what you are. Philosophical reflection. Feynman once said something that has always struck this channel as one of the most quietly profound statements a scientist ever made. He said that when you know something deeply, really deeply, from first principles, with genuine understanding rather than borrowed vocabulary, there's a pleasure to it, a specific, distinct pleasure that is different from anything else. He was describing the felt experience of neural integration, the sensation of understanding that has become so thoroughly woven into the fabric of your thinking that it no longer feels like information you hold, but like a way of seeing that you've become. The difference between carrying a map and knowing a landscape so well you no longer need one. That pleasure is not reserved for geniuses. It is the natural, biological reward your brain generates when you've done the work of genuine understanding. It is what the process we've described today is pointing toward. And it is, if Feynman's life is any indication, something that only gets richer, more frequent, and more deeply satisfying the more consistently you practice. The brain you have right now is not the brain you're stuck with. It is the brain you've built so far with the practices you've used so far. And beginning today, not next semester, not when you have more time, but today, you can begin walking new paths. You can begin building new trails. You can begin the quiet, gradual, profound work of becoming a different kind of thinker. That work is never finished. Feynman never finished it. He was still curious, still generative, still deliberately confusing himself with new problems right up until the end of his life. And he described that unfinishedness not as a frustration, but as one of the great gifts of being alive. The universe is enormously, inexhaustibly interesting. Your brain has the capacity to grow toward that interest without limit. The only question is whether you'll use the practices that allow it to. This is physics explained simply. If this kind of thinking, rigorous, accessible, grounded in wonder, resonates with you, there's a great deal more where this came from. Subscribe, explore the back catalog, and bring your most confusing questions with you. Because confusion, as Feynman knew better than almost anyone, is always the beginning of something worth understanding.